Morning, everybody. How we doing on this beautiful foggy morning? My wife and I are two very different people because where I get energized by fog and I just love it, she gets sleepy. So, different strokes for different folks, I suppose. We just finished simple harmonic motion. It was a blitz. I got some feedback from people saying, Mr. Bay, that was kind of hard. Like there was a lot of equations and a lot of ideas, and yes, you're absolutely right. It was a lot. But the nice thing about the toolbox is that it's done. It's solved for you. A lot of the difficulty we went through was to get those equations in the first place. Now that we've got them, if you can find omega, which is the hard part, finding omega can be the struggle. Once you've got omega, you've unlocked the entire toolbox, and it's just a matter of figuring out which equation to use to solve for what you need, which by this time you have that skill. So what we're going to do is we're going to take that idea of simple harmonic motion and we're going to extend it into space and time. What's a wave? Yeah, so let me ask the question slightly differently because but now you realize by now that I ask a bunch of annoying questions that we really can't answer, right? Like what does salt taste like? What's mass? What's a wave? Name things give me examples of waves, things that are waves.
Ocean waves.
Sound. Ocean. That is never the first one in Fresno. Right?
Yeah,
No, I heard light waves first, I think, followed by ocean waves, right? Is heat a wave? Yeah. Okay, what other kinds of waves are there? Light, ocean, heat, sound. We can name lots of things that are waves, right? But like how do we describe what a wave is, right? So what we're going to do is we're going to try to define that and define the terminology that we use, okay, and everything that's going on. And the way I want to do that is by pulling up a simulation. And that simulation should be right here. Technology work today. Okay, right? So this is a wave, right? Granted, it's a simulated wave, right? The computer's making it. But the advantage I can put that wave on this whatever this is. What is this? Spring, right? I can put that on this thing, but like maintaining it and stopping it and pausing it and all that kind of stuff gets a little bit awkward. So, and you guys are from a generation where if it's on the internet, it's real, so it's okay, right? So here we've got a wave, right? I'm going to take this wave and I'm going to slow it down, right? So that we can really kind of get an idea of what motion is happening in here. And did I bring... Oh. Does it work? Of course not. Yes? Okay. Very rarely do I use laser pointers because I always hate that when a teacher comes in and just reads the PowerPoint to you. And I think the first most vile sin a teacher can do is read a PowerPoint to you. The second is using a laser pointer while they do it. Right? Okay. So and yes, it is a mouse. Why is it a mouse? People don't steal mice. I can leave this in a room, come back, people are like, the mouse didn't work. I was like, yeah, I know, it's a laser. Okay. So what's going on here? So we've got, do you see how this thing is moving across the screen? Right here, okay? For you guys, these peaks right here, okay, are moving across. What is this down? If this top thing is a peak, what's this? A trough. Yeah, valley would be a good word, but unfortunately we don't use that one. It's called a trough. I am not responsible for the English spelling of this word. Because that's not how you spell trough. This is how you spell trough. Right? That says trough. This says true. Or trug. English is dumb, right? But my campaign for respelling is not taking off. Maybe that's the third executive thing I would do as if I was president. All sweats, no SUVs. Trough is now spelled T-R-O-F-F. Trough is how that's pronounced and spelled. It's the opposite of a peak. It's the valley of a wave, right? So we have peaks, we have troughs. The speed at which this peak is moving, any peak on here, just pick one, right? That peak right there is equal to the speed at which the trough is going, right? So did this wave have a speed? Is this wave going places?
No.
Yeah. It's moving, right? But let's try and answer. We'll get back to wave speed and other things and how we measure stuff. But let's get back to, instead, right? Okay. Let's take a look at this green dot right here. Take a look at the green dot that is right here, kind of in the middle of the screen-ish. Okay. If you watch, just focus on that green dot right there. What's it doing? Bouncing up and down. What do we call this? This is simple harmonic motion, right? That little green dot is a simple harmonic oscillator, right? It's got amplitude, it has frequency, it has period, it's got all those things, right? So, one definition of a wave is a set or a collection of connected simple harmonic oscillators. It's not a pretty description. But it is an accurate one. Because if you take any one of these individual things, right, and you watch it, what's it doing? It's doing a simple harmonic oscillation. But it's connected to its neighbors very elegantly. Are all of these oscillators doing exactly the same thing at the same time? No, right? They're offset from each other in where they are in their oscillations, giving rise to this pattern. Waves must have a medium in order to exist or propagate. If you try to send sound waves through the vacuum of space, it's not going to work because sound travels through air or water or glass. It has to have a material. If there's no molecules to wiggle up and down for a sound wave, you're not going to hear it. What we're going to do for chapter 16, this is chapter 16 now, is we are going to study the physics of waves in general, and then next chapter specifically we're going to talk about sound waves. So we'll kind of put off the sound wave stuff for just a little bit. All right, let's pause. Kind of put that thing into pause mode right there, okay? So we got to define some terms here. And what I want to do is, I used to be able to like take a picture of that and put it on my slide, but it doesn't work as well anymore to do that. So I'm going to cheat. That's not the cheat. That doesn't work. Okay, so we'll just bring this back and I'll just redraw it real quick. And this will be good because this will show you how to like sort of conceptually get a picture of a wave down on a piece of paper so that you can work with that. So we typically talk about waves moving along some sort of axis, right? And this is like the y-axis, this is like the x-axis. And then you can draw the wave. Now, it doesn't really matter if you start like drawing a sine wave or a cosine wave. It doesn't really matter. I typically, like when I'm drawing waves, I tend to start like as a sine wave, but you want to make sure that your wave kind of looks equal above and below the midline, the point of equilibrium. So if we were to measure this distance right here, the height of one of the peaks and the depth of one of the troughs, those are amplitudes, aren't they? Right? This is a carryover from our simple harmonic motion, right? What was another idea or concept we had for simple harmonic oscillator? We had amplitude, we had, what else? Frequency. Okay, so the frequency of a simple harmonic oscillator was the number of times it bounced up and down in 1 second. For a wave, the frequency is like if you're standing, say right here, okay, and you're watching and you're counting the number of peaks or troughs that go by you in 1 second, that would be the frequency of the wave. The problem with any piece of paper, be it made of electrons or, well, actually real paper is made of electrons, be it made of like, iPad screen or not, is that you can't animate the wave in time. A wave exists in both space and time, and we need to animate this sort of picture, okay? And so maybe we'll say that the wave speed, right, is moving to the right. So it has amplitude. Frequency would be the number of peaks, okay? Peaks or troughs, can't spell, per second. What would the period be? The period is the number of seconds. Yeah, between two peaks or troughs. Okay? So frequency is counting the number of peaks that go by per second. So if you see 10 peaks go by you in 1 second, what's the frequency? 10 hertz, right? 10 peaks per second. And the period of that would be 1/10 of a second. So the time it takes for one of those to go by would be 1/10, right? They're inverses of each other again. All right. Somebody mentioned the other word that is a new word. Yeah, wavelength. The distance between peaks or the distance between troughs. It doesn't matter what we measure, okay? It's called the wavelength, and that is the letter lambda. Have you seen lambda before in this class? No, not in this class? Okay, how do you draw lambda? It is the Half-Life logo. Thank you for that reference. That was excellent. Where'd my pen go? Right here. So the way you draw lambda is you draw a candy cane, okay? But the candy cane is falling over, right? Candy cane standing up, it's starting to fall over, and so it sticks its leg out to not fall, right? That's the Greek letter lambda. The short handwritten way to do it. Okay, so that's wavelength. What are the units of wavelength? Good, meters. Okay, frequency is in hertz. Period is in seconds. We know we got amplitude, and all right. There's a couple of other things I need to show you that I kind of just have to show you to be able to define them. I need a volunteer. Somebody who's willing to hold the other end of my spring for me. No, he doesn't. Don't keep throwing Malachi under the bus. Jack, thank you. Grab that. Stay there. Don't let go. Kind of hold it up a little bit. Okay, so I want you to notice something. This is my big slinky, right? Just hold on to your end. I'm going to send a pulse down, right? So what I did is I kind of sent a disturbance down the spring, right? It went from one end to the other, right? That's not a wave, okay? That's just a pulse. A wave would be a continuous train of pulses, okay? And actually, this is a very special wave that I've made right here called a standing wave. We'll get into it later, okay? Now, the other thing I wanted you to see, is your arm okay? Yeah. Well, the other thing I wanted you to see is that I can make what's called a transverse pulse, where the thing that travels along the spring, it's been like deflected at right angles to the direction it traveled. So that was a transverse wave or pulse. Now I'm going to do a longitudinal wave. No, I screwed up. Yeah, it is like P waves and S waves. Let's see if I can get it to... There we go. That one's better. Okay? There's supposed to be no transverse component. But what's traveling along the spring is a compression. Right? It's compressed together, and it's that compression that travels back and forth. Jack, put it on the floor. Let go. Thank you. Give Jack a hand, everybody. Sacrifice his life for science. Yes, good bow. That was excellent. There's shear and P waves. So shear waves in geology, oh my gosh. Shear waves move parallel to the surface of the earth. P waves, the primary wave, I believe, is the compression wave that travels from the epicenter. Did I pass? I never took a geology class. My uncle's a geologist, so I had to know these things. Okay. All right. So what do we got? We got wavelength. We've got speed. Wave speed. What are the units of velocity? Meters per second, right? So again, the speed at which a wave travels is referred to as its wave speed. The speed that a peak or a trough is moving is the speed of the wave. There we go. I said it correctly. All right. I'm gonna give you an equation now, and it's important that you understand something about this equation that is going to look very, very straightforward and simple. That one right there. It's kind of like one of the master wave equations, but, and here's the warning, it's a trap. It's a trap. Why is this one a trap? Too many people read equations too literally. For example, if I make the wavelength bigger for a wave, what happens to its velocity? If the wavelength goes up, what happens to the velocity? Increases? That is wrong. Okay? The speed of a wave doesn't change because the speed of a wave depends on only one thing. And it's not either of the things in that equation. Speed of a wave does not depend on its wavelength. Speed of a wave does not depend on its frequency. The speed of a wave depends on the properties of the material that the wave is traveling in. We say the medium in which the wave is traveling. Okay? So, the speed of a wave in water is different than a speed of a wave in air. Why? Because the medium is different. Not because the wavelength is different or the frequency is different or any of that kind of stuff. So that's why I say this equation, although true, you can find the speed of a wave by taking its wavelength, multiplying by its frequency. You can find the speed of a wave. The thing that will change the speed of a wave is when its medium changes or the properties of the medium change. Like if air gets denser because it's colder or less dense because it's hotter or whatever, right? If the properties of the medium change, then the speed of the wave will change. But the speed of a wave only depends on the medium. It does not depend on the wavelength or the frequency, which is why, again, I always call this equation a trap. Right. So, what is this equation good for? This equation is actually the relationship between wavelength and frequency. Because if the wavelength gets bigger, and what's a bigger wavelength look like? It means this distance is doing what? Getting bigger, right? So that wave would look, I don't know, something like that, like all stretched out, right? So this would be big wavelength, right? What would small wavelength look like? This is it thought that I was trying to erase by wiggling. I've done a terrible job of drawing it, but you get the idea, right? Okay? You alter the frequency of a wave, you alter its wavelength. Which of these has a higher frequency? I shouldn't call big wavelength. It's not the word we use. We say long wavelength. Okay? The distance between peaks is long. Which of these has a higher frequency? Yeah, short wavelength, high frequency. In other words, if the wavelength goes down and the speed is the same, because the only thing that affects the speed of a wave is the medium in which it travels, right? So assuming v stays the same, if the wavelength goes down, what does the frequency have to do? It has to go up. So this equation is a relationship between wavelength and frequency. They're inverses of each other. The bigger the wavelength gets, or the longer the wavelength gets, the shorter the frequency, vice versa. So again, be careful with that equation right there. There's a couple of other sort of toolboxy type equations that we can have. Did I write any of them down? Of course not. Why would I do that? Wait, are we already, what chapter are we in? 16. We are in 6. We're going to go straight into sound wave. I lied. Then what the heck are we doing in 17? Oh. That's what we're doing. Yes, we're going to do standing waves in chapter 17. Okay, so we are going to go straight into sound waves. But let's get down a couple of other things here before we get there. For a wave on a string, what part of the orchestra have I just described? The string section. Yeah. It's called the string section, okay, right? So we're talking about our violins, our guitars, our violas, right? Anything that you take a bow, right, and drag it across some string, right? That is a stringed instrument, and the sound is produced by vibrating a string, right? And on those strings, there'll be wavelengths and frequencies and all that kind of stuff. So for a string, the speed of the wave is going to be equal to the square root of the tension. I'm going to spell this out because there's too many T's everywhere, right? Okay. Tension divided by that. What is that not? It is not the coefficient of friction. Again, we're starting to recycle some of our symbols, okay? In this context, the speed of a wave on a string context, that mu is the mass per length of the string. Any guitar players in here willing to admit it? Anybody? Okay, so when you play your guitar and you want a low note, what kind of string do you reach for? Is it like thick or thin? It's a thick string, isn't it? Okay, and for the higher notes, you reach for a thinner string. If you look carefully at the guitar strings, they start thin and they get progressively thicker as you go down the neck. And so the thinner strings have a smaller or less mass to their length. And so they are able to sound higher frequencies, shorter wavelengths. The thicker the string gets, the more energy or force is required to get the string to vibrate, and it will simply sound a lower frequency, lower wavelength note. So the speed of a wave depends on the medium in which it's traveling, and for waves on a string, whether it be a musical string or a rubber band or anything, I mean, my slinky is a string, the speed will be determined by the tension. Higher the tension, so you tune a musical instrument, a string instrument, by changing the tension in its strings. You can change the speed on the string, which changes the wavelength and the frequency and so on and so forth, right? So that's what that mass per unit length is doing in there, right? The bigger the mass of the string in its length, the slower the wave's going to be going, so on and so forth. So again, just kind of handy equations to have in your pocket when it comes to talking about waves in general. Let's see, what have I got for you? Oh, the other thing I had to tell you. This gets mathy. Sorry. Okay. The function of a wave, the mathematical description of it, is the amplitude, and then this can either be sine or cosine, by the way, okay? Kx minus omega t. So this is the mathematical formula that gives us this shape right here, okay? I don't want you to worry so much about sine or cosine. You'll see it written both ways. A sine kx minus omega t and a cosine kx minus omega t. Don't worry about that, okay? Worry more about the pattern here that this equation is trying to tell you. So, and I'll do some examples of this, but if there's a number sitting right here in the front of this number was 10, what would you know instantly about the wave? Its amplitude is 10, okay? X and t are variables. They are not things that we generally know unless we're told, like a position and a time, that the wave is doing something. Okay? K and omega are constants for a given wave. K, it's not what you think it is. K is 2 pi divided by the wavelength, otherwise known as the wave number. Omega, well, omega is what you think it is, okay? It's the angular frequency that we had back from simple harmonic motion, okay? And omega is equal to 2 pi f, okay? I don't know why I wrote down the word is right here. K is 2 pi divided by the wavelength. Okay, so in this unit already, we've run into a couple of notation problems. What's K for a simple harmonic oscillator? Do you remember? For a mass bouncing up and down on a spring, what's K? Spring constant, okay, in Hooke's law. But when we start talking about waves, there aren't any springs in waves. Well, there sort of are. They're hiding in there, right? But the K is called the wave number, and it is literally 2 pi divided by the wavelength. I'm sorry. I didn't make up the rules, right? I guess I'm perpetuating the problem, but there's no. So some books will actually write this function down, and it'll look really, really scary because they'll write a sine 2 pi divided by lambda times x minus 2 pi ft. And your brain just kind of goes, right? Because there's just too much in there. A lot of physicists write K and omega. We call K the wave number, and we call omega the angular frequency. The speed of a wave, right, is equal to lambda times f. If we kind of substitute in that lambda is equal to 2 pi over k. What did I do there? If I move the lambda up and I move the k down, right? Or multiply both sides by lambda and divide both sides by k, whatever, however you want to think about it, right? Then I can write lambda is 2 pi over k. And then what is f? It's omega over 2 pi. What happens to the 2 pi's? Cancel. So another way to write the equation up in the box up there is omega over k. Where again, omega is the angular frequency and k is the wave number. Now, why am I telling you all this, and why am I telling you about the function of a wave? This makes it really easy to tell what's going on, say, if you know the mathematical description of the wave. What is this wave's amplitude? 10 meters. Okay? If you're not given any units, you assume SI units for all these things. Okay? Okay, so we know the amplitude's 10. They didn't ask me to find that, but I found it anyway. Speed, wavelength, and frequency. They want V, they want lambda, and they want F. How the heck are we going to do that? Well, What do we know about the number that's sitting right here in front of the x? The number sitting right in front of the x is k. Good job. Right? What's the number that's sitting in front of the omega, the t? Thing sitting in front of the t has to be omega, right? So this right here is k. That right there is omega. K is equal to 2 pi divided by the wavelength, right? So the wavelength will be 2 pi divided by k. Well, that'll be 2 pi divided by 2 pi over 3, which happens to be 3. And since it's a wavelength, what unit am I going to use? Meters. So there's the wavelength, 3 meters. Okay. Frequency, well, omega is equal to 2 pi f. So that means that the frequency is equal to omega divided by 2 pi. The omega in my problem is pi over 6, and I'm dividing by that by 2 pi, which gets me, was that 1/12? And what are the units? Frequency. Nope. Frequency. Not angular frequency. Hertz. There we go. And now that I know both the wavelength and frequency, what can I find? I can find speed. Because it's going to be lambda times f, which is 3 times 1/12, which is 1/4, isn't it? Is 3 divided by 12? Yeah. 1/4? Meters per second. I also could have used, what was it? Omega over k. Omega over k, which is pi over 6 divided by 2 pi over 3, which is the same as pi over 6 times 3 over 2 pi, pi 3 to 1/4 meters per second. Right? If you can read the mathematical function of a wave, you can find out its wavelength, you can find out its frequency, you can find out how fast it's going, you can find out its amplitude. It's all sitting right there in a compressed package. You can also go the other way. You can determine the mathematical description of a wave if you know something about it. Okay? So, it says this wave has an amplitude of 6 meters. Okay? 0.6. Okay? So, amplitude is equal to 0.6 meters. Great. Period is 1.5 seconds. Wavelength is 2.5, right? Now they want us to find the function, right? And remember, the function has a pattern, a sine kx plus or minus omega t. That's what I forgot to teach you over here. This is a plus or a minus. Okay? If the sign is a minus between those two things, the wave is moving to the right. Once again, I'm not responsible for how the laws of mathematics work in our universe. If you plot this function and you give it x's and t's, then what will happen is the peaks and troughs will move to the right if you put a minus sign in there. If you put a plus sign into that function, the peaks and troughs will move to the left. I'm sorry it's backwards. It's how trig functions work. I will not be held responsible for trigonometry or our human understanding of it. Okay. So, since they tell me that this thing is moving to the right, what sign am I going to pick here? Yeah, I'll pick the negative. So I'm going to do f of x of t. Okay, so I'm going to do 0.6 sine. I've got to figure out what k is, but I'm going to use minus omega t because it's going to the right. That minus sign means it's going to the right, not night. Right. That didn't fix anything. Okay. All right, so how do we find k and omega? K is the wave number, right? K is equal to 2 pi divided by the wavelength. We know the wavelength, don't we? 2 pi over 2.5, which is that 5 halves? Yep. So that's equal to 4 pi over 5. You might be like sitting here going, Miss Bale, why don't you just use your calculator to get the decimals? You can. It's fine. Okay? But quite often in wave physics, we tend to work in the multiples of pi because it's more precise that way. All right. So now I know my K. How do I get my omega? Omega is equal to 2 pi f, but they didn't give me the frequency, did they? They gave me the period. What's the relationship between period and frequency? They're inverses of each other, right? So this is 2 pi over the period. Back from straight out of simple harmonic motion, right? So this is going to be 2 pi divided by 3 halves. So that's going to be 4 pi over 3. All right, so now I can come up here and finish my function. It's going to be 0.6 sine, and then I'm going to put in my k, 4 pi over 5 x minus 4 pi over 3 t for the omega, and there's my mathematical function. I can go and I can plot it and see exactly what this wave looks like, what it's doing, all that kind of stuff. Can I find out how fast this wave is going? Yeah, we've got k and we've got omega, we've got wavelength and frequency, right? We can, like the toolbox for waves, right, is sitting here with the boxed things that you see, right? And if we can, there's no really unlocking this one, okay? Unlike simple harmonic motion where you are forced to find omega, this is more of a, okay, what do you got and what do you want to know? And here's the pattern, right, that fits mathematically for a wave and the different things. I think there is a learning curve here, it's kind of steep when it comes to the vocabulary and the symbols, because again, we're starting to recycle symbols and they mean something different depending on the context, right, for what's going on. It occurred to me after this last exam, I don't know why it's taken me this long into the semester to remember to do this. On your next test, I'm going to put the topic of the question right on the question. Whoa. Right? Thank you. So the topics list that I'll publish for you, right? It'll give you the topics. You'll see that same wording at the end of a question, right? So let's say I ask you to do a wave function or something, right? The topic wave function. The question on the exam will have something, and at the very end in italics, it's just going to say wave function, topic wave function, right? So that way, it just helps a little bit, I think, with the context of things as we start recycling some of these symbols. Because this test is going to have K's on it that can either be simple harmonic motion, like Hooke's law, spring constant K, or it could be wave number K. And how do you tell? Well, again, it all comes down to context, and having the topic right there, I think, will probably help you remember which context you're in. It won't stop your brain from still freaking out, but it'll be a little bit more helpful. All right, so being able to write down the function based on the information that you're given, or if given a function, can you figure out what's going on? By the way, what direction is this wave going? It's going to the left. How do you know? It's got a positive in it. Okay? So, and we talked about this already. I showed you this transverse versus longitudinal. Okay? The reason we distinguish, and there's other kinds of waves, by the way. There's torsional waves and elliptical. There's a bunch of different kinds. But we'll just talk about transverse and longitudinal. The reason we distinguish between them is because the type of wave is determined, again, by the properties of the medium and kind of how a medium responds to being pushed or pulled in certain directions. So the speed of wave on a string, I already told you, right? The speed of a wave in air has a different equation. Now, this equation doesn't seem to get used as much anymore, and I don't understand why. It's not wrong. Maybe it's not as precise as some of the other equations that they're using in textbooks now. But the problem is like the equation in your textbook, I didn't even bother to write it down, has like the bulk properties of the air, like what pressure was the air and what was its buoyancy and like what's its favorite political party, and like I was like, I don't. And we skipped over to the thermodynamics section where we would have learned all of that stuff. So ignore your book as far as finding the speed of waves in air. Use this instead. 331 meters per second times the square root. Oh golly, here's another t. T over 273 Kelvin. Okay, there's a lot of problems with this equation, and I am sorry. Okay, that T up there is temperature in Kelvin. And I know we haven't done thermodynamics yet, and so technically you're not supposed to know like what the different temperature scales are and all that kind of stuff, but here's the short version. Kelvin is Celsius. It's just zeros in a different place. Okay? 0 degrees Celsius is 273 Kelvin. So if you're told the air temperature is 27 degrees Celsius, what are you going to do to get it into Kelvin? Add 273, or ask Google, or write it down on your cheat sheet, right? Temperature in Celsius, temperature in Kelvin equals temperature in Celsius plus 273. Okay? So I'm not going on a test, I'm not going to ask you to calculate this. I'm giving you this equation in case a problem says, well, the air temperature is 45 degrees Celsius. If it's 45, you're dead. And, what's the speed of sound in this air? Now you can just do it without having to like calculate the pressure or do anything else. Okay? I should write down that temperature in Kelvin is equal to temperature in Celsius plus 273.15. I keep hearing all the chemists yelling at me. 273. That's good enough. Okay. So what is the speed of air? Speed of sound, because it's the speed of any wave in air is the speed of sound. A wave in air is sound, by definition. So if it's freezing outside, if it's 32 degrees Fahrenheit or 0 degrees Celsius, how fast is the wave going? If the Celsius temperature is 0 degrees, how fast is this wave going? This one isn't hard. What's 273 over 273? No. 1. What's the square root of 1? 1. What's 331 times 1? Okay. And then what is the speed of sound if, say, we're at like room temperature, which is, we can argue about room temperature all day long, but typically is like 21 degrees Celsius. It turns out that that's roughly 343 meters per second. So if you are not told the speed of sound in a problem, assume 343. Some books will say just 340. It actually doesn't really make that much of a difference between 340 and 343. Okay? So if it's a sound wave, and you're not told the temperature or the speed that it's traveling, just assume 343. Okay? If they give you a temperature, you have to go calculate what the speed of the wave is. Or if they say, in a certain situation, the speed of sound is 329 meters per second, right? Then you know what it is, right? And you can keep going with your calculations, right? But again, the speed of a wave depends on what? The medium in which it travels. And air changes its density with temperature, which is why we have to kind of, futz around with it. Again, there's a T there. And how do you know that's temperature? Because of context. Because it's being divided by a temperature in Kelvin. Speed of sound on a string I already did, but let's just lay it back down again. What's this T right here? This is tension. That's the force of tension in the string in newtons, right? And what's this? Not the coefficient of friction. What is it? It's mass per length, right? Kilograms per meter. Watch out. They'll try to fool you. They'll give you the unit. They'll give you the mass per unit length in like grams per centimeter or something. So what do you have to do? Got to convert. All right. So we're just kind of laying out a lot of the toolboxy type equations for different kinds of waves. Okay. We're going to segue specifically into sound waves. And first thing you need to know about sound waves is that they are longitudinal waves only. So transverse and longitudinal was all about what direction was the wave wiggling compared to the direction it was traveling. Air can only do longitudinal waves because air is a fluid. Now, usually when we use the word fluid, we're talking about a liquid, right? But in physics, fluids are both gases and liquids, okay? And in gases and liquids, waves travel as longitudinal waves. Let me prove it to you, okay? We're going to take a look at the restoring force on an air molecule. Okay, how is it connected to other air molecules and what happens if we try to squeeze on it or move it, okay? So I'm going to capture an air molecule. That one. Got it, okay? Now, if I pull this air molecule down, so it started right here, and I start pulling it down, can you hear it screaming? And when I let go, I want you to watch where the air molecule goes, right? You ready? What did it do? Did it spring back to its location? No, it doesn't care, right? I can take an air molecule, right? I can push them all around. They don't care, right? They'll just move to the new spot. There is no restoring force in the transverse direction. However, if I take a bunch of air molecules and I squeeze them together, okay, I have to keep squeezing because what are they doing? They're pushing back, right? And if I let go, then they will spring back, right? They don't really like being crushed up against each other. They want to get back. That's a longitudinal restoring force, okay? And so that's why waves in fluids travel as longitudinal waves, not as up and down like waves on a string or a spring, but rather as a series of compressions that's coming at you. So my voice, as melodious and amazing and James Earl Jones that it is, right? As it comes from my mouth to your ears, what kind of wave is it? Longitudinal or transverse? Longitudinal. How do you know? The medium that the sound is traveling in is a fluid, right? Now, can sound travel in solids? Yeah. In the glass, in the railroad tracks, whatever, okay, through the walls. It can do that. It generally does it, though, as a longitudinal wave. It can be transverse, because solids have a transverse restoring component, but generally keep doing it as longitudinal ones. But it can be different. Okay. Don't write any of these down, but I give you like, just to show you a table, right? The speed of sound in various materials is well known. You can go look it up, right? You don't necessarily have to calculate it, right? If you ever wanted to know what the speed of sound was in carbon tetrachloride, I don't know why you would want that. Don't drink carbon tetrachloride. Don't breathe it. Don't go anywhere near it. It's terrible stuff, okay? It causes it melts nerves or something. It's not good, okay? Why would I want to know the speed of sound in mercury? Don't do anything with mercury, right? But we got air, we got oxygen, hydrogen, helium, all kinds of different stuff. You can go look it up, right? You could see there that they're giving it at certain temperatures, right? You see how air at 20 is 343? and air at 0 is 331, right? That came out of that equation that we have. Thinking about sound waves can be a little bit tricky because they're waves, right? They have wavelength, they have frequency, but trying to like draw that on the page, trying to imagine like what the sound from my mouth is doing as it gets to your ears, it's not easy to draw as wiggles. Especially, like how do you draw a longitudinal wiggle? I mean, I can do a transverse wave, pretty simple, right? But how do I draw that? That doesn't really communicate anything, right? I mean, it's a barcode, Mr. Balogh. Like, what is that? Right? It doesn't look like a wave at all, right? And it certainly doesn't communicate any kind of motion or anything like that. So what we do is we kind of back off from like the literal. We know it's a longitudinal wave because it's traveling in air and air is a fluid, right? But wink, wink, we tend to draw them as transverse waves. Or we go one further, and instead of drawing like waves, we'll draw these rays. Please don't panic. These are not vectors. Okay? I know. Terrible things have been done to you by me, right? But that's not a vector, okay? That is an arrow that shows the direction of propagation of the wave, right? We're trying to in our visualization, we're going to try and take a little bit of the wiggle away. We know it's a wave, we know it's longitudinal, but we're going to talk about like wave fronts, and these are modeled as coming off as concentric spheres. So like as I speak into the room, the sound emits from a point, but that sound immediately begins to spread out like a sphere, where my mouth is the very center of that sphere and it goes out, right? And as those waves travel through the air, coming at you as a series of compressions, right? They spread out into the room spherically. And I can draw the rays that sort of give me the direction of propagation for that wave, and so on and so forth. So this is kind of a model that we use. Again, models help us to see abstract ideas. They may not literally be what's going on. Think of a model like if you've ever had anatomy and physiology and they give you that model of the eye. They don't give you this little tiny model that's like, to scale with the eye. They give you, right? It's supposed to like be scary and freak you out because big eye. Right? Okay. But that model is not the literal thing, right? Because most eyes are smaller than that. But it's nice and big for you to be able to take it apart and identify the layers and do whatever it is they want you to do in anatomy and physiology, right? In physics, our models kind of do the same thing, right? Only our models sometimes don't look anything like what we are trying to describe. Instead, the model is helping our human brains picture something that is very real. It's just we kind of go, wink, wink, it doesn't really look like that. But this gives us predictive power to be able to go what's going on. Okay? Speaking of models, right? It's time to talk about how these flappy things on the side of your head work. Because this is really what sound is all about, isn't it? It's our interpretation of these waves. We can talk about how the wave travels through the air till the cows come home, but it loses all of its meaning if we don't understand what's going on biologically with our ears and our brains and all that kind of stuff. So first of all, I am not a doctor. I just play one on TV. I don't do that either. But now that I don't watch The Pit. I don't think I could like survive watching The Pit. But I've watched doctors analyze The Pit. Apparently it's the most accurate medical drama on TV when it comes to like what they were doing. So. But I'm not a doctor. Okay. What is this? I mean, what is that? That's the snail that lives in your head, right? It's called the cochlea. Apparently it's got a name. I don't know why his mother picked that name, but that's what it is, okay? Okay. What is the big flappy thing? What are these for? Ears. These are not ears, actually. The ear is what starts on the inside of your head. What's this for? Catch sound? Okay, let's do an experiment, right? I am going to do my best to keep up a steady monologue of talking constantly so that you can pull off the following experiment. Take both of your hands and put them behind your ears like this, like cupped behind your ears, and then take them off and put them back on again as I continue to talk and try to keep exactly the same volume and exactly the same amplitude in the room. Can you hear any difference between when your hands are over your ears versus when your hands are not over your ears? Hurt your head? Well, you should sit back. No. What was the difference?
Louder.
It was louder, wasn't it? Even, not just louder, but it got like crisper, right? Okay, same experiment, only slightly different. As I keep up this constant drone of sound, I want you to take your ears and I want you to pin them to the side of your head, like really push them back so that they're flat against the side of your head, and listen to the difference between having them pinned to the side of your head versus having them not pinned to the side of your head. Did you hear it? What happened if you pinned? What happened to the sound? It like got muddier, right? It got quieter. That's because the outer ear, these flappy things on the side of your head, are designed to collect the sound waves and channel them into your ear canal. The ear canal exists for you to put very small objects in and then try to fish them out. Don't ever do that. Don't ever do that. People seem horribly fascinated with putting small objects in their ears, right? Like Q-tips and all that kind of stuff. Do you know what the American Medical Association, the American Pediatric Association's guidelines are for the size of an object that should go into your ear if you are not a doctor? This is true. I'm not lying. This is how they write it. The object should be bigger than your elbow. That's what it says. Now I can, a bunch of people are. And this is the point, right? If it's smaller than your elbow, does it belong in your ear? No. Right? Because anything smaller than your elbow, you run a risk of causing damage to the rest of the hearing complex. Okay? In the ear canal, if you scrape it, you can get bacterial infections that can actually lead to death. Like it can get into the bone and then gets into your brain, sayonara you. Okay? Earwax, very necessary. Don't try to just dig it all out. It needs to be there to protect your ear canal. Okay? Don't put your finger in there. Okay? Don't put a Q-tip in there. You start pushing all that wax, it can interfere with the tympanic membrane or the eardrum. You can actually puncture the eardrum if you're putting the wrong stuff in there. Just don't do it. But amazingly, sound gets collected by the flappy. Well, there's a name for that. What is it? Pinna? P-I-N-N-A? Thank you. I walked out of anatomy and physiology. So, right? And then the pinna collects it, sends it down the ear canal till it gets to the tympanic membrane. What's the job of your eardrum? To vibrate. It collects. So the sound comes out of my mouth, travels through the air, right? My vocal cords in here are flapping and banging together, okay? Causing those interruptions and compressions, right? And relaxations of the sound waves. It's called a compression and rarefaction. I'm not responsible for that word either, okay? And it goes by, right? Compression, rarefaction, and then rarefaction means spreading out. And so then your ear collects it, goes down the eardrum, and it hits your eardrum, right? Okay? So whatever the pattern of sound, right, that I'm saying gets onto your eardrum, and your eardrum takes that and starts to wiggle back and forth. The thing is, eardrums can't wiggle back and forth very well. They're just really just a membrane. There's a flap of skin, okay? And a flap technically isn't connected. Your eardrum's supposed to be connected all the way around. And so evolution has come up with a really clever system of amplification. This is mechanical amplification, requires no electricity for this to work, okay? And there's 3 bones. The hammer, the anvil, and the stirrup. What were they actually called?
The malleus, incus, and stapes.
Thank you. I'm glad. Anatomy and physiology? Yeah, you're right there. Okay, right? So they together, in the way that they are shaped and how they're connected together, take a very slight wiggle of your eardrum and actually like make it bigger. Amplifies it. And then finally, it couples to the cochlea. Okay? The semicircular canals up there, those are your in your head accelerometer. Okay? If you close your eyes and you move your head back and forth, you can kind of know like where your head is in space. Okay? Vision is actually the primary system that you use to tell where your head is in space. Okay? But when you're denied vision, you can do that. By the way, motion sickness, okay, comes about because the snail in your head is saying one thing, okay, the semicircular canals, which is literally like an XYZ axis in your head, okay. The fluid sloshes around in them and you can tell where it's tilted. If the semicircular canals are telling your brain one thing about where your head is, and your eyes are telling you something different, like your eyes can see that you're moving, but the fluid in your head says you're not moving, okay? Does anybody know why you get so violently ill? No? Okay. Your brain is a pretty simple organ in one sense of the word, okay? When it detects a discontinuity between systems, the visual system is saying one thing, but the ear is saying another, your brain goes straight to the assumption that you have been poisoned. Because a sign of poisoning is a disconnect between what you're like feeling and seeing and all that kind of stuff. And how do you solve poisoning? Empty everything out of all orifices as fast as possible, right? Throw it up, poop it out, do something, right? The body's going to respond the way the body's been trained to poisoning, right? And so motion sickness, that sickness you feel, is the same that you would get if you ingested something that was poisonous and your body systems started freaking out because it can't tell, different signals or cross signals, and now it's just going to try and eliminate the cause of the problem, right? So that's why you get sick with motion sickness. Okay, so what's the cochlea do, right? Well, the cochlea, inside of the cochlea, there's a whole bunch of little tiny cilia. These are little tiny hairs. And at the base of each one of those hairs is connected to a nerve ending. And the length of the hair corresponds to a certain resonant frequency for sound. Remember we talked about resonance and if you push it just right? Well, the length of these hairs, the longer ones pick up longer frequencies, the shorter ones pick up shorter frequencies, and they're clustered. They do all kinds of stuff in there, right? But they'll wiggle inside of this fluid that's inside the cochlea. They'll wiggle inside of that fluid based on what frequencies it's hearing. And then those frequencies, the nerve ending goes, oh, frequency heard, sends it to your brain, and then your brain spends a whole lot of time trying to put all the information together. So why does it take so long for a child to learn how to talk? Like, what's going on? Why don't they come out of the womb just spouting Shakespeare? They haven't heard it yet? Okay. Takes a while for the brain to process all of that information about frequencies that they are hearing and put those frequencies together in a pattern that's a word, like a sound trough, as an example, right? Like, what the heck does that mean, right? It just takes the brain a while to realize that a sound has been made, right? Now, here's the really interesting thing. This is independent of culture, right? Different cultures have different sounds, different language structures, and that's all very defined. Asians have a lot more ability to hear different sounds than Americans do because the Asian languages just have a lot more distinct sounds in them as opposed to our American, hey, what's up, dude, right? I speak really good Californian. But what is the same, independent of culture, that unites us as all human beings, well, besides the belief that everybody has that they are an above average driver, is that you give any adult a baby and they will turn into an idiot. What do I mean? If you give any adult a baby, what do? What do? Baby talk. Oh, what just happened? Right? This went from a high functioning adult to what the heck? Right? Why? Why does this happen in every culture, anywhere? What's going on? What have we been programmed to do for our children? Babies aren't stupid. Babies are pretty smart. They know exactly what they want and they know how to get it. Okay? And they manipulate the adults into making it happen. Okay? But what does the baby need to learn? What's going on to the voice of an adult when they're talking to a baby? It's going through the entire range that the human voice can create. When I talk to you, I don't make it all cute to you. Boo, 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 boo. Isn't this physics amazing? If I walked in on the first day doing that, you'd be calling security, right? How do adults talk to each other? In a pretty monotone, standard set of frequencies. Even if we get excited, oh, what just happened? The frequencies kind of went up. They got louder, but they didn't go like as high as if I was talking to a baby, right? So we have this evolutionary response to help infants and children understand the great range of the human voice so they can make sense of all this stuff. I don't know why I'm talking about it. This is really fun. Okay? So what happens when it goes wrong? Yeah. You end up not being able to hear stuff. Okay? There's a lot of reasons somebody might not be able to hear things. But the one that we're able to fix is when there's problems with the cochlea. Okay? If there's a breakdown in the ability of the ear to get the wiggles into the cochlea, but the cochlea is still connected to the brain, right? With the nerve endings going into the brain. Then you can have something called a cochlear implant. It's literally something that goes inside the snail in your head, okay? And what it does is usually there's something wrong with the connection between the outside world and getting to the cochlea. Something somewhere, okay? And so an hearing aid, the part that sits next to the ear, okay, is listening to everything in the outside world, okay? And then the cochlear implant through a little magnetic thing they got not a port, but they've got a little magnet on their head, right? Okay, and they put it on there. And what it does is it transmits the signal from the hearing aid to the implant that's in the cochlea. And so then the implant in the cochlea causes the vibrations. It stimulates the cilia inside of the cochlea, and then the body's natural, nerve endings and everything takes over to enable these people to hear. And people with hearing loss or hearing disability, especially if they were born with it, right, have trouble usually with the sound of their speech. You'll hear it, they can't quite make the sounds correctly because they're unable to, they haven't heard the correct frequencies and all that kind of stuff. So I want to show you a clip, okay, of a woman who was given a cochlear implant. This is not the screen that I want. I did a really bad job of setting that up. That one, thank you. Okay, so this is a video from YouTube of a young woman who, if I remember the story correctly, she had lost her hearing in her teen years, okay? I don't know what the issue was. I'm not going to remember, so I'm not going to say. But she had lost her hearing. She had been born hearing and then lost it during her teen years, okay? So this is her getting fitted for her cochlear implant for the first time. She's had the surgery, the implant's in, and now they're trying to calibrate, right? And hook up the device for her to be able to hear for the first time.
It's so clever.
That's the audiologist helping her.
Right over
Got to get the connection just right.
There you go. Beeping. So now technically your device is on. Can you tell? Oh, that's exciting. Or you can put it down for a second. Just get used to the sound. What does it sound like?
Stop asking your stupid questions. Her husband was taking the video, and she had never heard her husband's voice up until this moment. We live in Star Trek, right? Like we live in an age when there are hearing loss or vision loss that can now be corrected. Not everybody, right? We're working towards that day when we can improve the quality of life for everybody. But just this week, I was reading about an experiment that was going on. I think it was in Europe. Maybe I got that wrong. But they had fitted patients with a very tiny microchip that was embedded in their retinas. These are people that had lost their vision. They didn't say why. I didn't read that closely. But then they had a pair of smart glasses that they wore, and now they are able to read words off of a page. Like I said, we live in Star Trek. I've watched videos of kids who are blind that are given special glasses, right? They're not smart glasses. They're just glasses that give off like bat echolocation. And then the kids have something, they have like things in their ear that like it'll beep or whatever. It'll make a sound, okay? And these kids learned how to like navigate a room just by like sweeping their head back and forth, and the glasses would send the beeps to their ears and they could tell. The video is of them running around playing tag in the playground. Totally blind. Sign me up. Let's make it happen, right? Let's make all of this stuff happen because it can't happen fast enough. I got distracted, but it's good stories and it's good times. I will continue with sound intensity and the Doppler effect, so like how loud sounds are and how we measure that. Oh, fair warning, next Tuesday, logarithms. No. Yeah, we got to use a logarithmic scale. I'm sorry. No. It's going to happen, okay? So we'll do sound intensity. We will do Doppler effect, and we'll do breaking the speed of sound, and that will be the end of chapter 16. But that's okay. We have 2 days for chapter 16, right? And we'll make it. We'll make it. If I don't see you in Grasp, have a great weekend.